Welcome to NASA Edge, an inside and outside look at all things NASA. We're joined by Michelle Munk and Steve Gaddis. How you guys doing?
Great.
And we have a very important topic today, and that's going to be EDL, or Entry, Descent, and Landing. Now, Michelle, you're the Principal Technologist for EDL.
Yes.
What is Entry, Descent, and Landing?
Entry, descent, and landing is how we get a spacecraft from the top of an atmosphere to a planetary surface. So the entry part refers to, the atmospheric flight, most of it, and then we have descent and landing, which is usually propulsive and get us down on the surface safely. We do D and L at places that don't have atmospheres like the moon or, asteroids. But usually we talk about EDL when we talk about atmospheres.
So Michelle, what is your role as Principal Technologist for EDL?
I look across all the missions that NASA has coming up that will use entry, descent, and landing on any planet. And I look at the technologies we're going to need for those missions, and I bring them forward to the mission directorate for starting funding. So
you have a need in the EDL world, in the community. You're coming up with the technologies that are needed for future missions.
Right.
So you take some of those technologies that maybe are less mature, hand them off to you.
Right.
And then you mature those technologies.
Design, develop, test, and evaluate.
Is that a pretty easy task, trying to figure out
not at all.
what technology you're going to need?
Not at all. I have to look at both the human missions that are coming up, so sending humans to Mars.
Right.
I have to look at the scientific missions that are coming up and all the destinations the scientists want to go to, and I have to kind of rank those and prioritize them and figure out where they are in terms of maturity and what the best infusion point will be. When is the first mission that can use that technology? And then I have to figure out what is the best program within STMD for the investment. Is it better to have a university work on it, or a small business, or is it better for a game-changing program element?
And your job is really hard, because we're going to be talking about a suite of EDL projects over the next two shows, because there's so much content in EDL.
There's a lot of content.
We can't do this into one show.
Absolutely.
So this will be part one of two parts. So how do you manage all that?
Well, one is it's hard, but it's also fun. Okay. And we've got excellent technologists leading every one of these activities, so we all work together. And we all know that we need these technologies, so we're motivated to see them be successful.
We're a very passionate community.
Yes.
I've seen that in all the interviews that we've done. You guys are definitely passionate. Now, the first one that we're going to be talking about is ESM, or Entry Systems Modeling. What is that about?
So that's the first part of it, where they develop these models and simulations to understand how the technology works and how it will be beneficial at a system level. It's very cross-cutting against all the projects, and the plan is to take that data and then infuse it into the projects.
Blair had a chance to go out to NASA Ames Research Center to talk to Mike Barnhardt, who is the Integrated EDL Systems Lead. Let's check it out.
Mike, tell me a little bit about Entry Systems Modeling Project. What is it?
So the Entry Systems Modeling Project is tasked with developing a lot of these technologies that are coming from lower technology readiness level, things like academia, and trying to bring them up to a level so that we're ready to help them.
So in this particular situation, we're talking about EDL projects, and so you're actually helping them raise their technology readiness level?
That's right. So any of these things, Orion, Mars 2020, Mars Insight, anybody that's flying anywhere in the solar system and they need to enter an atmosphere, you have to go through an entry, descent, and landing phase. And we don't have all those problems solved. We don't have all those technologies built. And so we're continually trying to improve on our existing technologies and also renew with new ideas. And that's the real purpose of the Entry Systems Modeling Project.
How do we get the data we need to improve the EDL process across these missions?
Right, so there's a lot of different things that we can do. We have ground facilities, which we rely on a lot. So we have arc jets that we do for material characterization and developing models for material response. We have our shock tubes, which we use to develop radiation models. We have wind tunnels that we use to build aerodynamic models, the dynamic motion of a body as it's flying, that sort of thing. We need to know all that in order to have a successful entry into a planetary atmosphere. So that's the simplest thing that we have access to every day. And then we also have, some amount of flight data. So there was the Orion EFT-1 flight last year, which was very successful, and we can use that to take our models and look at our predictions and then try and back out, exactly how well are we doing, quantify, how well are we predicting that.
You used a lot of data from the Apollo era. Are you able to use data from things like MSL and more recent missions to help? Because I know we have limited data on entry.
Yeah, so MSL is a really great example because we flew Medley on MSL, and that allowed us to get some of the only data that we've had on entry at Mars. So heating data, pressure data, which we use to reconstruct the aerodynamics, is fantastic tool for us, but there's a lot of challenges there as well. So it's really, it takes a village. You need to have your computational models because they're the only thing that's going to access the true flight space that we have here on the ground. We have ground facilities that simulate parts of the flight space. And then ultimately you have a little bit of flight data. And your goal is ground to flight traceability. Let's predict what we do on the ground. Let's predict what we do in the air. And let's see, how far apart are we so that we can quantify when we're designing the next mission exactly where we think we'll be.
Are you sharing that data with all the different EDL potential systems that are being developed?
Absolutely, absolutely. Everything that we do in the Intersystems Modeling Project is, for the greater good. We work very closely with academia. So we've got university partners that we are sharing this data with to help improve our models. We share it with other projects. So with radiation modeling, we were working very closely with the INSIGHT project and OSIRIS-REx projects because they had issues with radiative heating on their back shell. So they call us because we're the radiation modeling experts and they say, here's our problem, tell us, how worried do we need to be?
Be worried, be very worried.
Yeah, we're always looking to help everyone else around the agency, and that's really what Space Technology Mission Director is all about, right? Is trying to help the other directorates with the technology that they're going to need.
Tell you what, great interview with Mike Barnhardt. I mean, it really kind of gives you the flavor of how difficult EDL really is.
Right.
I mean, if you can't characterize it and model it here on the ground,
Yeah.
I mean, you'll never be able to land.
That's right.
And you can't test an entry system on the ground and get the flight-like data that you need to design.
And that's the challenge but with Medley on MSL, that was a game changer, wasn't it?
Absolutely.
I mean, you actually, for the first time, were able to actually see the health of the spacecraft as it was entering the atmosphere.
Yeah.
Right. As engineers, it's great that we succeeded, but I want to know if I got an A+ or a C- on the design. So the Medley data allowed us to actually know how we designed the vehicle.
And based on that Medley data, what were the results? They were pretty good, weren't they?
They were
excellent.
fantastic. But we found some things that we didn't know. Radiative heating is important at Mars and at the scale of MSL. We didn't recognize that before.
And now, since it was such an important mission for you guys, now you're going to take it to the next level for Medley 2 for Mars 2020.
For Mars 2020, yeah, we've got that going, and they're right in the middle of their preliminary design phase.
Right.
They're all excited. They're going to put some new measurements on the back shell.
Yeah, they were actually at Aberdeen Proving Ground last week doing some testing to see where to put the pressure measurement on the back of the vehicle.
Right.
So yeah, it's really exciting to get this new data in the back shell and using new sensors.
We know Blair had a chance to sit down with Mark Shoenenberger, who's the reconstruction lead, which I got to ask you about that when we come back, because I never heard of a reconstruction lead, but we're going to learn more about Medley 2. Let's check it out.
So Mark, when we think about the differences between Medley 1 and Medley 2, it's interesting because Medley 1, the M stood for MSL, Mars Science Laboratory. Now it's Mars 2020. You guys caught a break. You get to use the same letter.
We still get to use the same letter. I think it'll just be shortened to Mars, EDL instrumentation, and it'll hopefully continue for a bunch more Medleys, Medley 3, 4. We can always call it Mars.
Perfect. It's a nice little series you got going.
We're getting great data. So.
Now I'm wondering though, in terms of technology and in terms of how you're growing Medley, I mean, Medley 1 was a very successful mission as far as the data we got back. What are we expecting for Medley 2?
For Medley 2, it's really to dig in and look at the pieces that we couldn't quite get for Medley 1. The instrumentation there was it was the first time we'd flown instrumentation since Viking to get pressure and heating data. So we really tried to capture the whole event. And to do that, especially for pressures. We had these transducers that could see the peak high pressure as you went through the hypersonic phase, and you're really slowing down around Mach 18. And then as you slow down, you really start getting in the noise there with the kind of information you can get. The signal was just really weak. It's sort of like using your bathroom scale to measure the ingredients for a cake. It's just, there's not a lot of resolution there. So it's tough. You don't really trust those measurements.
That's about how my cakes turn out, as
right.
if I measured ingredients with it.
So what we did here now is to use more of a postal scale for pressure. So we're measuring down at the low range when we're flying supersonically. Right as we get near parachute deploy, we're spending a lot of time just kind of slowing down, flying at the same altitude, but you're really at terminal velocity. You're not slowing down real well.
Now, is that pretty much in the part of the descent, if you will, that where you've burned away most of the heat shield that you're going to in the process?
Yeah, all the heating's over. It's still a little warm and things are kind of winding down, but yeah, all the exciting heating stuff is over, and you're really just trying to bleed off energy until you get down to a condition that's safe for the parachute. And so any error in your prediction of how that vehicle slows down, or your prediction of what the atmosphere is going to end up being on the day at Mars, can lead to being far uprange or far downrange. Your landing ellipse and how you target it, you need to account for that. So if we can get better data to characterize the aerodynamics, we can tighten that up and land in even smaller spaces.
Which is always the goal, right? You're
Yep.
trying to find out exactly where you need to land.
Yep.
So Mark, how is the instrumentation different on Medley 2 from Medley 1?
So, at least from my experiences with the pressure side, Medley 1 was really designed to capture the pressure all the way through entry. So it had this nice high maximum pressure it could measure. What we really wanted to do for Medley 2 was to look for the low pressures right before chute deploy. We're going to be coasting there, slowing down from, say, Mach 4 down to Mach 2 for a minute, 100 seconds, something like that. And that adds to the landing ellipse, any error in aerodynamics. So the transducers, we put more of them on the heat shield, and they're at a lower range, so they'll have much better resolution at those low speeds. So we can pull out things like winds, and we can get a better estimate of the drag. And we also have a pressure transducer on the backside. As you slow down, get down to supersonic speeds, the pressures on the back shell become a big contributor to the total forces acting on the capsule. And it's really hard to predict, actually, what those pressures are. So with some truth on the backside, that can really help us nail down the total behavior of the capsule as it's flying at those low speeds.
It seems like we're getting an awful lot of good data on the things that are happening during EDL and Mars, especially for Medley and Medley 2. Are we able to, in the future, maybe translate what you're doing here to potential different atmospheres or different EDL circumstances?
Absolutely. So Medley 1 definitely demonstrated, and it was the reason I think we have Medley 2, was it became the model of how you put an instrument package on a heat shield, how to work with the project to do it, so that they're not scared about putting holes in their pristine heat shield that's designed to keep their rover on the ground. We have a process now to do that. So you'll see missions going to Venus or Jupiter, Titan, those kinds of things. They'll all have instrumentation during entry, and NASA has the confidence to require that because we did so well with Medley 1, and hopefully again with Medley 2.
Mark did a really nice job discussing Medley 2, but I have to ask the question, in all my years at NASA, talking to subject matter experts from all 10 centers, what is a reconstruction lead?
Reconstruction is really important after a flight
Okay.
to understand exactly how and where the vehicle flew.
Oh, okay.
And without the proper data, it's really hard. You have to make some assumptions.
Okay.
So for instance, before Medley, when we didn't have an independent pressure measurement, we had to assume something about the aerodynamics of the vehicle in order to figure out how it flew.
Okay.
Now with that independent pressure measurement, we can nail it and we don't have to make any assumptions. So reconstruction lead is really key to understanding how we did.
See, you learn something new every day. I had no clue.
Yeah, he comes back up with that flight plan that
Right.
they had and where the data is along those flight plans. It's very important.
Now, speaking of that flight plan, with Medley 2, can you take the data from Medley 1 and kind of show what the flight plan is going to be for Mars 2020, or is that a completely different flight plan?
It's a lot the same because it's the same shape, size, vehicle. The mass will probably be a little different. They're using the same entry, descent, and landing system, but the atmosphere obviously will be a little bit different. The entry velocity will be a little bit different because of the different year.
Right.
But largely, you know, we're going to use all of our MSL simulations as the basis for where we start on 2020.
No, I know, Steve, with game changing, you take technologies and you take them from a technology readiness level. We always talked about that 1 through that 9 scale.
Yeah.
And you're in that middle range.
Middle range, about 3 to 5 or 6.
Right. So, but with Medley, since you have proven you have a flight underneath you, and then you're working on Medley 2, is that still considered,
Yes.
technology at that level?
Yeah,
It's still not space ready.
Yeah, and
it
was like what Michelle was telling you was we learned so much through Medley 1 that we want to put different kinds of transducers to get the lower pressure range. We want to understand the back shell pressures and radiation rates. So we learned so much, so it's not really just a repeat of Medley 1.
Yeah, we have totally new sensors. Knowing what we know from Medley 1, we've moved a lot of our sensors, so we have kind of the same number of channels of data, but we've distributed them differently on the forebody and then moved some to the back of the vehicle.
Well, speaking of a new mission, we also have now, instead of Medley 2, we also have HIAD 2.
Yep.
Absolutely.
Which is a hypersonic aerodynamic inflatable decelerator.
Inflatable aerodynamic, yes.
We did it again. It's a hypersonic inflatable aerodynamic decelerator.
Yes.
Bravo.
Very cool.
Bravo.
All right, so that's a completely different type of EDL system from Medley 2.
It is.
And Franklin had a chance to sit down with the project manager, Joe Del Corso.
Yes.
And we're going to learn more about HIAD 2, so let's check that out.
So Joe, we're talking about HIAD 2. Tell me what has changed since HIAD 1.
So we've had a number of changes. The first one was we upgraded our thermal protection system. In HIAD 1, we used a Generation 1 thermal protection system, which was somewhat capable. It's low temperature capable, basically something on the order of 1,000 to 1,100 degrees Celsius on the surface. For HIAD 2, what we've looked at is much higher temperature capable materials, much more flexible and lighter weight. So now we're using custom built silicon carbide materials as an outer fabric. We're using COTS materials and some custom materials for our insulator systems. And then on the backside for the gas barrier, you have woven fabric systems with PTFE film wrapped around it. Our inflatable structure is also being upgraded. And then the other thing that we're doing is we are working on scalability. We're focusing on trying to get to a 12-meter scale. In order to do that, we've got to upgrade a lot of our equipment. We've got to work on something as simple as just picking up one of the gore seams. It takes a lot of development, a lot of careful coordination. So what we're focused on is not just upgrading our materials, but also upgrading our handling techniques, our manufacturing techniques.
Tell me about the HIAD timeline from the time it was conceived to where we are right now with HIAD 2.
So HIAD has been in development, previously it wasn't known as HIAD, but it's been in development now for almost a decade, and we still have probably another 4 years worth of work to do to get us to human access to Mars. We started out in 2006 doing material testing, and really all we were doing is we were doing low-level, trying to learn how to test fabric systems so that we could simulate an atmospheric entry condition. We were learning how to learn in the early phases. We had ERV-1 happen. Unfortunately, there was a launch vehicle anomaly, so we lost that. But what it did do is enabled us to put in place ERV-2 flight tests. People had enough confidence in what we were doing that they allowed us to build a build to print. That went up on a sounding rocket, launched out of Wallops, and it was an incredibly successful proof of concept. We had an inflatable structure, but no real TPS at the time, thermal protection system. Following the success of ERV-2, we started up what we currently know as HIAD, which is the Hypersonic Inflatable Aerodynamic Decelerator project. During that project, we were doing all the lab scale development, small scale, little samples, We had learned how to do the initial testing. Now we were taking it through a maturation process, getting it ready for flight again. The third flight that we flew out of Wallops again was called ERV-3. That was a much higher heating condition, and it was the first chance for us to actually test a thermal protection system with our inflatable structure. After the success of ERV-3 and the closure of the initial HIAD, we attempted to fly an orbital entry flight test called THOR, the Terrestrial HIAD Orbital Reentry Flight Test. Unfortunately, due to the ORB-3 failure, we had to cancel THOR and we went back to a ground development effort. But unlike the first two ground development efforts, the third one wasn't focused on learning how to test or testing materials or developing materials. It's focused on scaling. So we did small scale in the early development phases, and now we're scaling to something more applicable for human access to Mars.
Now, the cool thing I understand about HIAD 2, that you guys have a partnership with ULA.
Yeah.
Let's talk about that.
So about a year ago, ULA announced that they wanted to use HIAD technology to recover their boosters as part of their new business model, affordability. And so we've been working on a flight demonstration with them over the last year and a half.
Yeah, and that would be at the 6-meter scale, which is about halfway to what ULA would need for their full booster recovery, 12 meters that Joe talked about on the video. And it's also the right scale for us to do maybe a technology demonstration mission leading up to putting humans on Mars.
So the idea is that you're using this HIAD technology to recover the first stage of a ULA rocket. And so is that going to be recoverable, and is that going to sort of land in the ocean? Is it going to land on dry land? How is that going to work?
They actually want to snatch it out of midair with a helicopter and to minimize any refurbishment costs.
Wait a minute, so you're going to have this booster coming down with the HIAD deployable shell.
Yes.
And then a helicopter's going to come and just kind of grab it
mid-air retrieval. Yeah, it'll come in. It'll have a catch hook, and the helicopter will come. It's a modified helicopter, obviously. But that's the plan.
Yeah, we've not air snatched anything of that mass yet, so that's a little bit of technology development as well.
Wow, I seriously hope that you go back to your ESM folks and do some modeling of that snatching, because I
reconstruction of the booster trajectory.
Reconstruction. So the reconstruction lead will be a part of that too.
Absolutely.
That's perfect. Well, we're looking forward to seeing that in action, because that will be something to see when that actually happens.
That would be awesome.
And also with HIAD, which is a win-win not only for ULA, but for NASA. NASA gets a demonstration out of it, but then it kind of matures that technology to move on to an eventual test on Mars?
Yes.
Awesome. I tell you what, we've come to the close of just part one of EDL. I mean, we've covered a lot of technology today, and on the next show, we're going to be covering even more technologies.
Yeah, we should be talking about Adept and 3D Mat and heat.
And now, with regards to 3D mat and heat, that's more of the material side as opposed to the big system side, isn't it?
Right.
I'm looking forward to that, and so stay tuned. We're going to be talking more about EDL. You're watching NASA Edge.